So this lesson we're going to start looking at springs. And springs are kind of cool because as you stretch a spring, the force required to continue to stretch the spring increases. And ideal springs obey a rule that's called Hooke's law. What that basically says is that the force applied to a spring increases as the spring compresses or is stretched. It also goes one step further to say that the amount of compression or stretch is proportional to the force. Basically, the larger or the more stretch or compression you give, it requires more and more force. The force always acts opposite direction of your stretch or compression. So if I pull this ball out here with this ideal spring, the force that the ball would experience due to the spring is toward this way, toward the left. So X is to the right, the force is to the left. If I were to push the ball in on this spring, it would experience a force toward the right. And so if I were to pull this out and let it go, what's going to happen is the ball is going to go this way, go past what we call the equilibrium position. Where would the ball be sitting if the spring was unstretched? It would compress the spring. Ball feels a force in the opposite direction. It's going to get pushed this way. Stretch the spring until we get to this maximum stretch, and the ball is going to start to move this way. To define that force, I calculated as negative K, which is called the spring constant, times X. And K is usually given in a unit newtons per meter. The negative sign basically indicates that force and displacement are in opposite directions. So let's look at the frequency of the oscillation for a spring. Can we define frequency in terms of things that we might be able to calculate it with a spring? Something like the spring constant. So let's use Newton's second law and Hooke's law. What I know is that the force acting on an object, net force, is m times a. Well, if that force happens to be a spring, I know that force is equal to negative k times x. So I could write the relationship m times a, the net force acting on my object, is equal to negative k times x. That it's the spring that's causing the net force. Now if I solve this thing, or if I plug in what I know from the previous lesson about how x and a look in terms of functions of time, I get a sine of omega t times k and times negative k equals m times negative a omega squared sine of omega t. Now the one thing to point out is in both of these I have an a, which is going to cancel, I have a negative sign which will cancel, and I have a sine of omega t which will cancel for both of these as well. So I have three different variables which will cancel, and I'm left with m times omega squared equals k. Well, that's kind of cool because if we remember about what omega looks like from the previous lesson, omega is related to frequency and frequency is related to period. So this would suggest that I only need to know two things about the spring in order to figure out the frequency of its oscillation: the mass that's connected to the end of the spring and the spring constant k. If we actually solve this out for omega, divide both sides by m, square root both sides, omega is equal to k over m. Well, if period is 2 pi over omega and frequency is omega over 2 pi, we could use those results to figure out what are period and frequency in terms of k and m. Frequency should be 2 pi divided by omega. Well, if you invert omega, square root of m over k. And frequency should be 1 over 2 pi times the square root of k over m. Basically, as the mass gets bigger, the period increases. As the mass gets bigger, the frequency decreases. As your spring constant gets larger, the period decreases. As your spring constant gets larger, the frequency increases. So these are some pretty helpful relationships. If I don't know k for a spring, if I know the period, I could find a relationship between period and k or frequency and k. So let's do a quick example problem. And here I have a spring that is stretched by 0.018 meters when a 2.8 kilogram object is suspended vertically from its end. And it says how much mass would be attached to the spring so that it will oscillate with a frequency of 3 hertz. Now the first thing that I probably need to do is figure out what k is. Since frequency is equal to 1 over 2 pi times the square root of k over m, I need to know k to find m. I know what frequency is, it's 3 hertz, but I need to figure out what the k is in order to answer this question. So the way to figure out what k is to apply Hooke's law. Sum of force equals 0, kx, mg. So if this is true, then kx minus mg must be 0 if a 2.8 kilogram object stretched the spring 0.018 meters. So I can actually solve it out for k. mg equals kx, k equals mg divided by x, so k must be 1524 newtons per meter for this spring. Now I can solve my other equation for m. Multiply 2 pi to both sides. square everything to get rid of the square root. It looks like I want to multiply by m to get the m out and divide by 2 pi over frequency. And what I'm left with is 4.3 kilograms is the mass that we need to put on there. So it's kind of a quick overview of a quick problem dealing with Hooke's law and our formulas for frequency or period, and how we can use those to start to work some problems.